Okay, so hi and welcome to your CPE 6101, Computer Engineering as a Discipline. Okay, so this topic discusses week 6, specialty areas of computer engineering. Okay, so there are many specialty areas in the field of computer engineering. Okay, so we have coding, cryptography, and information protection. Okay, so computer engineers work in coding, cryptography, and information protection to develop new methods for protecting various informations such as digital images and music, fragmentation, copyright infringement, and other forms of tampering. Okay, so examples include work on wireless communications, multi-antenna systems, optical transmissions, and digital watermarking. Okay, so cryptography is the practice and study of hiding information. Okay, it is the art or science of converting a plain intelligible data, okay, into an intelligible data, or what we call encryption. And again, transforming that message into its original form, or we call it decryption. Okay, so it provides confidentiality, integrity, and accuracy. Okay, so when we say cryptography, it is derived its name from Greek word called kryptos, which means hidden secrets. Okay, let's discuss types of cryptography. Okay, so we have symmetric key cryptography or the secret key cryptography. So I said this is an example. You will notice you have the plain text and then undergo the encryption, and it will now be a ciphertext. After that, it will go under the decryption, and it will now be again a plain text. Okay, so same key is used by both parties. Of course, we have advantages and disadvantages. So the advantage, simpler and faster. Then the disadvantage, less secured. Why? Because same key is used by both parties. Of course, we have the other one, which is the asymmetric key cryptography or public key cryptography. This is an example. You will notice we have Bob's public key, and another Bob's private key. Okay, so two different keys are used. Okay, so users get the key from an certificate authority. And of course, we also have advantages and disadvantages. Okay, so let's start with the advantages. More secured. And of course, authentication. And for the advantages or disadvantages, relatively complex. And then let's move to the next specialty areas. We have the communications and wireless networks. Those focusing on communications and wireless networks work advancements in telecommunication systems and networks, especially wireless networks, modulation and error control, coding, and information theory. Okay, we also have the high-speed network design, interference suppression and modulation, design and analysis of fault-tolerant system, and storage and transmission schemes are all a part of this specialty. Then we have compilers and operating systems. So this specialty focuses on compilers and operating systems design and development. Engineers in this field develop new operating system architecture, program analysis techniques, and new techniques to assure quality. Okay, examples of work in this field include post-link time code transformation, algorithm development, and new operating system development. And next, we have computational science and engineering. Okay, so computational science and engineering is a relatively new discipline. So according to the Sloan Career Cornerstone Center, individuals working in this area, computational methods are applied to formulate and solve complex mathematical problems in engineering and the physical and the social sciences. Okay, so examples include aircraft design, the plasma processing of nanometer features of semiconductor wafers, VLSI circuit design, radar detection systems, ion transport through biological channels, and much more. Okay, so computational science and engineering is a relatively new discipline that deals with the development and application of computational models and simulations, okay, often coupled with high performance computing, of course, to solve complex physical problems arising in engineering analysis and design, or what we call computational engineering, as well as natural phenomena, or what we call computational science. Okay, so computational science and engineering has been described as the third mode of discovery, which is next to theory and experimentation. Okay, so we have computational science and engineering methods and frameworks. Okay, this includes high performance computing and techniques to gain efficiency, of course, through change in computer architecture, parallel algorithms, etc. Okay, we also have modeling and simulation. Then algorithms for solving discrete and continuous problems. Analysis and visualization of data. Mathematical foundations such as numerical and applied linear algebra, initial and boundary value problems, Fourier analysis, optimization. Data science for developing methods and algorithms to handle and extract knowledge from large scientific data. Okay, so we also have computational science and engineering applications. Okay, this can be applied to aerospace engineering and mechanical engineering, astrophysical systems, battlefield simulations and military gaming, homeland security, and emergency response. Can also be applied to biology and medicine. Okay, example is the bioinformatics. Then we have chemistry, civil engineering. Okay, example is the finite element systems or finite element analysis. And of course, computer engineering, electrical engineering, and telecommunications. Examples are VLSI, computational electromagnetics, and semiconductor modeling. And of course, we can apply computational science and engineering in many, many more. Okay, so let's go back to these specialty areas. So we also have computer networks, mobile computing, and distributed systems. So in this specialty, engineers build integrated environments for computing, communications, and information access. Okay, so when we say distributed system, it is a computing environment, okay, in which various components are spread across multiple computers or other computing devices on a network. Okay, so these devices split up the work, coordinating their efforts to complete the job more efficiently than if a single device had been responsible for the task. Okay, so examples include shared channel wireless networks, adaptive resource management in various systems, and improving the quality of service in mobile and ATM environments. Some other examples include work on wireless network systems and fast Ethernet cluster wired systems. Okay, so we also have computer systems, architecture, parallel processing, and dependability. Okay, so engineers working in computer systems work on research projects that allow for reliable, secure, and high-performance computer systems. Okay, so computer architecture includes CPU design, cache hierarchy layout, memory organization, and load balancing. So projects such as designing processor for multi-threading and parallel processing are included in this field. Okay, so other examples of work in this field include development of new theories, algorithms, and other tools that add performance to computer systems. Then we have computer vision and robotics. In this specialty, computer engineers focus on developing visual sensing technology to sense an environment, representation of an environment, and manipulation of the environment. So the gathered three-dimensional information is then implemented to perform a variety of tasks. Okay, so these include improved human modeling, image communication, and human-computer interfaces, as well as devices such as a special purposes cameras with versatile vision sensors. Then embedded systems. Okay, so individuals working in this area design technology for enhancing the speed, reliability, and performance of systems. Okay, so embedded systems are found in many devices from a small FM radio to the space shuttle. Okay, I'll just explain something about embedded system. Okay, as its name suggests, embedded means something that is attached to another thing. Okay, so an embedded system can be thought of as a computer hardware system having software embedded in it. Okay, so an embedded system can be an independent system or it can be a part of a large system. An embedded system is a microcontroller or microprocessor-based system which is designed to perform a specific task. Okay, so for example, a fire alarm is an embedded system. It will sense only smoke. Okay, so an embedded system has three components. Okay, so it has a hardware. Okay, it has an application software, And of course, it has a real-time operating system, or what we call RTOS, okay, that supervises the application software and provide mechanism to let the processor run a process as per scheduling by following a plan control, okay, to control the latencies. So RTOS defines the way the system works. Okay, it sets the rules during the execution of application program. Okay, a small-scale embedded system may not have RTOS. So again, we can define an embedded system as a microcontroller-based, software-driven, reliable, and real-time control system. And according to the Sloan Cornerstone Career Center, ongoing developments in embedded systems include, okay, we have automated vehicles and equipment to conduct search and rescue, automated transportation systems, and human-robot coordination to repair equipment in space. Next, we have the integrated circuits, VLSI design, testing, and CAD. Okay, so this specialty of computer engineering requires adequate knowledge of electronics and electrical systems. Engineers working in this area work on enhancing the speed, reliability, and energy efficiency of next generation very large scale integrated circuits, or VLSI, and microsystems. Okay, an example of this specialty is work done on reducing the power consumption of VLSI algorithms and architecture. Next, signal, image, and speech processing. Computer engineers in this area develop improvements in human-computer interaction, including speech recognition and synthesis, medical and scientific imaging, or communication systems. So other work in this area includes computer vision development, such as recognition of human facial features. And we also have quantum computing. Okay, study of a non-classical model of computation. So whereas traditional models of computing, such as the Turing machine or lambda calculus, rely on classical representations of computational memory, a quantum computation could transform the memory into a quantum superposition of possible classical states. So quantum computing is the study of how to use phenomena in quantum physics to create new ways of computing. Okay, so quantum computing is made up of qubits. So unlike the common or the normal computer bit, which can be 0 or 1, a qubit can be either of those, or a superposition of both 0 and 1. Okay, so quantum computers can be used in taking large manufacturing data sets on operational failures and translating them to combinatoric challenges. Okay, that, okay, when paired with a quantum-inspired algorithm, can identify which part of a complex manufacturing process contributed to incidents of product failure? Okay, that's all for my discussion today, class. Thank you and have a nice day.